Now, so we are going to prove this result. The set of real numbers is an uncountable set. So we need to define what is meant by countable and what is meant by uncountable. So here, this is the definition. So S is a set. So we say S is countable if one or two happens. So it depends on the size or the number of elements in S. So the first case is when S is having finite number of items, and we call it a countable set. So this is easy, okay? Countable means that we can count the items one by one. So if it is finite, let's say it has 5 elements, so I can count the first one, and then the second one, the third one, the fourth one, and the fifth one, okay? But then more interesting is the second one. So it says that S is countable if there exists a one-to-one correspondence between the items in S and the items in N. So here N is 1, 2, 3, 4, 5, the natural numbers. Is that okay? So what is meant by a one-to-one correspondence? So if there is a one-to-one correspondence between S and N, then we can say that, okay, there is a certain item in S that corresponds to 1. Okay. So by looking at 1, I can go to that element of S. And then there is an item in S that corresponds to the number 2. So when I go to the number 2, I can find that item in S. Is that okay? So in that case, if I look at the numbers in N 1 by 1, 1, 2, 3, 4, 5, 6, 7, 8, then in that case, I will be looking at items in S 1 by 1. And eventually, every item in S will be seen. Is that okay? Because there is a one-to-one correspondence. If a certain item in S corresponds to the number 1000, then it will be seen when I'm looking at the number 1000. Is that okay? So in that case, you can actually think of S, the items in S, you can count it. Okay, so this is the first one, and then this is the second one, this is the third one, and so on and so forth. We will always count out all the items in S. We will not miss out any of them. Okay, in that case, S is called a countable set. Okay? Good, okay? So if this is the case, then we will usually call the size of S is equal to a strange label. This is called Aleph0, okay, or Aleph0. So this Aleph is a Hebrew character, so the first Hebrew character. So Aleph0. So as you can imagine, so there is Aleph1, there is Aleph2, and so on and so forth. Okay. So Aleph0 is like a concept of infinity, but there is a concept that is even more than the infinity. So we have Aleph1. So there is something that is even larger than infinity 1, then we have Aleph2, and so on and so forth. So this is the basic infinity that we have. Okay. Okay. Now, so we have defined what is countable set, right? So let us take a look of some examples. So these are some examples that I can come up with, and then we can actually show that this is correct. So first of all, this is the set of all even numbers. Okay, so let's make it simpler. All positive even numbers. So this is not finite, right? So the set of all positive even numbers is not finite. So to show that it is countable, we need to find a one-to-one correspondence between N and this set. Okay? Now, it's easy. To get the correspondence, it is easy. So if you look at the number 1 in N, I'm going to look at 2 in this even number. I'm looking at 2 in N, I'm going to look at 4. So I just double the number that I'm going to look at, then I will be looking at all the even numbers, all the positive even numbers. Is that okay? So if you're okay with this, could you please raise your hand? Okay, good. How about this one, the set of all integers? Now integers, it includes 0, it includes -1, it includes -2, and so on and so forth, right? So how can we count them. So I need to find a way so that each of these positive or negative integer, I'm going to see it. Okay, is there a way? So the numbers that I'm going to look at, I will have 0, 1, 2, 3, 4, blah, blah, blah. I will also have -1, -2, -3, -4, blah, 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 right? Now, this is a superset of the n. It contains even more items than in n. But still, we want to find a one-to-one correspondence. Good. So the idea here is that as long as you can find a one-to-one correspondence, that is okay. So as long as you can describe how you are going to list out the items here, then you are telling me what is the correspondence. So one way to do this is, let's list out 0 first, and then list out 1, and then list out -1, and then list out 2, and then list out -2, and so on. But actually, it is much easier. Let's do this. We have these two lists, right? I list out 0, and then I list out -1. And then I list out 1, and then I list out -2. And then I list out 2, and I list out -3. And so on and so forth. I go up, down, up, down, up, down, up, down, up, down. So what is good about this? We will see that no matter how large your number is or how negative your number is, it will be listed. It will be listed. Then in that case, well, in that case, this is a countable set. Is that okay? Although this one-to-one correspondence is more difficult to describe, but you can still describe it. Okay, so for instance, so you just go to, if it is odd, then it is going to be positive. If it is even, then it is negative. Okay, so it is like so strange. If you really want to list out, so it is like if it is, so you take the number n, you -1 if it is odd. Okay, wow. You try to divide it by 2, take the floor. Is it okay? And then times -1 to the power n -1 to the power n modulo 2 something like this. Okay? Whatever. Okay. So you can still list out. But this is not required. We are not going to specify a closed form of the function that you are going to map between n and the elements in here. As long as, the most important thing is, as long as you can find a way to list out all the items that you want without missing any one of them, then it is good. This is a one-to-one correspondence. Is that okay? Okay, so the closed form is not important, as long as we can list them out. Okay? Now, so this one is a special case of this one. So if we have a union of finite number of countable sets, finite, let's say k is equal to 10, then what we can do? So we have countable sets, 10 of them. So we can, let's say we have countable sets 1, we have items S1, S2, S3. So we can list out. This is the first one, the second one, the third one. And then let's say S11, S12, S13. And then the other one is, let's say the second one, the second list, S21, S22, S22. And then let's say we have finite number of that, finite number of countable sets. SK1, SK2, SK3, and so on and so forth. Then we can list them out in this way. This is going to correspond to 1, 2, 3, 4, k, and then k plus 1, k plus 2, and k plus k. Something like this, right? We can list them out one by one. And just in case if some item you have already listed, maybe 2 lists have common items, then what do we do? We just skip it. For instance, maybe this item is listed before, we just skip it. We give k plus k to the next one. So in that case, we can still list out all the items in all the lists without any problem. You don't miss anything. Is that okay? Is that okay? So we have now proven this one, and actually this one. Is that okay? So 2 is a special case of this one. Okay? There are just 2 lists of countable sets. Now, how about the third one? The subset of a countable set. Okay, so countable set, there are two types, right? One is finite, one is infinite. If a subset of a finite countable set, then it must be finite. So it is by definition countable. Okay. And a subset of a countably infinite set, if it is still finite, then it is still countable. So what we are concerned is, if it is having infinite number of items, but then it is still a subset of a countable set, then what should we do? So for instance, one special example is like, it's like prime numbers. Prime numbers is a subset of n, right? Prime numbers, we may have 2, 3, 5, 7, 11, 13, 15, 17, 19, and so on and so forth. So this is prime numbers, right? So how can we get a label? So the label is very easy. I give label 1 to the smallest one in this set. I give label 2 to the second smallest one. I give label 3 to the third smallest one, 4th, 5th, and so on and so forth. Is that okay? So in general, so what happens if we are looking at the subset of a countable set? Okay, so a subset of a countable set, so maybe we are looking at, so let's say S is a countable set. So we have S1, S2, S3, and so on. Such that this label 1, 2, 3 is according to the correspondence to the integer n. Okay, so this is the first item, this is the second item, and the third item. So if I have a subset S prime, so maybe I'm going to look at what? Si1, Si2, Si3, and so on and so forth. So let's say we are going to collect the items that we are going to look at. Then I'm going to list out the one with the smallest index here, smallest subscript here as the first item. And then 2 corresponds to the one with the second smallest item, second smallest subscript. Is that okay? So I'm going to find out which one corresponds to the smallest one here. The earlier that it appears in S, the earlier that it appears in S prime. That's what we are going to do. So eventually, if we can list out all the items here, then we must be able to list out all the items here. Is that okay? Okay? If we can list out a certain item here in the K step, we must be listing out that item here in S prime in less than or equal to K steps. Is that okay? Yeah, because some of them are missing. So we may list them out earlier. Okay? For instance, if originally we are going to list out 7 in N in the 7th step, 1, 2, 3, 4, 5, 6, 7. But here we are listing it out in the 4th step. Is that okay? Good. Okay? So far, if you understand what I'm talking about, could you please switch on? Okay, good. So this one is done. How about this one? The set of all rational numbers. So for simplicity, let's consider all positive rational numbers. Okay. Now, if positive is done, then negative is also done. And then we just union them, then we get all the rational numbers. So we just need to show positive. Okay. Now, rational numbers. So what is a rational number? It's like P over Q, right? For integer P, Q. So here, we have a very interesting way to list them out. So we are not going to list out this rational number directly. We are going to use the result of 3. We find a superset that contains all the rational numbers. And then we show that that superset is countable. So in that case, the rational number, which is smaller, which is a subset, will be countable as well. Is that okay? Okay, so we are going to look at this as simple. So we are going to look at things like 0 over 0. Well, okay, whatever. Okay, and then we have 0 over 1, 0 over 2, 0 over 3, and so on and so forth. We will then have 1 over 0, 1 over 1, 1 over 2, 1 over 3, and so on. And then we have 2 over 0, 2 over 2, 2 over 3, 2 2, 2 over 1, 2 over 2, 2 over 3, and so on. Is that okay? And then for the kth row, we will have k over 0, k over 1, k over 2, k over 3, and so on and so forth. Okay. Imagine, and this one does not necessarily represent a valid number, but we'll see that all rational numbers will be contained in this infinite size table. Is it? Because if I want to get 2 over 5, then it is going to be 2 over 5. Is that okay? If I want to find 17 over 3, then I will go to 17 over 3, and I will get everything. It contains more, but it will not contain fewer. Okay? And moreover, so for instance, some of them, if you treat them as numbers, then 1 over 1 will be equal to 2 over 2. But never mind. Okay? So if we are looking at rational numbers, and then if we have listed out this one, then we just don't list out this one later. Find it as a subset. Now, as long as we can show that all the items here, we can list them out in a systematic way, one by one, so that none of them is missed, then it's okay. Then it is going to be countable. Then what we are going to do, so we're going to list this as 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that okay? We are going to list them out like this. Is that okay? So we list out all the things so that the top part and the bottom part adds up to 0. And then we list out all the things so that the top part and the bottom part adds up to 1. And we list out all the things that is the top part and the bottom part adds up to 2, and so on and so forth. Is that okay? So 17 over 3, then when will it be listed? So after we list out all the things such that the top and the bottom adds up to 19, and then for somehow, it will be listed in that case. Is that okay? And then for any P over Q, we can see that it will eventually be listed, because there are only finite number of ways to have the top and the bottom adds up to P plus Q or fewer. Is that okay? So any form P over Q will be listed. Is that okay? So in that sense, this is still a countable set, because we can list out everything. So this is still countable. And the rational numbers, positive rational numbers, is a subset of this one. Is that okay? So positive rational numbers, maybe we are taking this one, this one, this one, this one, this one, and so on and so forth. Maybe this one. So this one is already taken, so we don't take. So it is going to be a subset of this one. And then a subset of a countable set is going to be countable. Okay? If you are okay with this, could you please raise your hand? Excellent. And so this one is done. And this is actually a special case of this one. The union of countably infinite number of countable sets. So we have the first countable set, the second countable set, the third countable set. We have countably infinite number of countable sets. So we can list out the items of all the sets here, the union, like this, in this way. Is that okay? So this is also done. Okay.